This is 2.3 Fatigue and Recovery by Sam Bynes. There are three different types of fatigue. The first one is local, which is in the muscle and it's a localized feeling of fatigue, and this is due to repeated contractions with no recovery, such as a bicep curl, so constantly curling with no rest in between. There's general fatigue, which is post-exercise, where you feel like physical or psychological weaknesses and fatigue. And then there's chronic, which is due to overtraining with not enough recovery, and this may give you a weaker immune system, which obviously means you're more likely to get an illness. There are different determinants of fatigue. The first one is intensity and duration. So for example, when you play different sports, like a 100-meter sprint, it's a high intensity and low duration. And then you could be doing a marathon, which is a lower intensity with a higher duration, and they'll make you fatigue in different ways, like how you're feeling. Then there's different fuels that you're using, depending on the intensity again, and whatever type of sport you're playing, and then you'll be getting different waste products as well with the different types of exercise. So the first one is 100 meters. This is a max intensity and a short duration, where you'll be using fast glycolytic muscle fibers. The fuel you'll be using is ATP and PC stores, and then the waste products be maybe lactic acid. What causes the fatigue in this type of exercise? Well, the ATP will run out after a while, after a few seconds, and then you'll not have enough energy, so you have to use the PC stores. But as you can see in the graph, as you start to exercise from rest, the PC stores will drop and will be depleted, and will need to be replenished as it shows in recovery. The methods to prevent decrease in PC are supplementation, taking creatine supplements, which helps increase the total work done. As you can see in the graph, the one in the black is the athlete that's taken some creatine supplement, and it's showing that it's got the total work done is higher in bout 1 and bout 2 than the athlete that hasn't taken anything. So maximal exercise recovery. So oxygen deficit, that's the difference between oxygen uptake during early and late stages of exercise, and it's what the body requires. The body requiring oxygen than what it actually takes. Then there's the EPOC, which stands for excess post-exercise oxygen consumption, which is the extra oxygen needed after exercise to restore the systems to normal states. And then for the recovery, there's the alactic fast recovery system. So that's the extra oxygen used to restore ATP and PC stores, and it also replenishes myoglobin and hemoglobin. This lasts about 2 to 3 minutes and requires 3 to 4 litres of oxygen to complete the component. The next one is moderate intensity exercise. So it could be 400 or 800 meter sprint or run. This is a moderate duration with a moderate intensity. This is more continuous exercise because it's not really stopping or at all. And the muscle fibers you'd use is the fast oxidative glycolytic, and the fuel will be carbohydrates converted into glucose. The waste would be lactic acid because of the long duration, and the ATP and PC used. The lactic acid needed will then form glucose to pyruvate through glycolysis, and that can be used for energy. So the OBLA and the lactate threshold. The lactic acid is waste, and this is what causes the fatigue in muscles. And as you can see in the OBLA graph, OBLA stands for onset blood lactate accumulation. And as you can see, the lactate threshold occurs, and that's when the lactate begins to build, and when the OBLA occurs, it begins to rise still. And then the lactate threshold is when it builds up, and sprinters occur rapidly, as you can see on the graph, the lactate threshold graph, that rapidly compared to the marathon runner, and then the middle distance runner is in between due to the amount of energy they're using and how much waste they're producing. So the lactate accumulation, the acidity will rise because it's lactic acid, and then the pH will decrease in the blood and the body, and then this means the enzymes won't be on optimum level of acidity, so then less ATP can be created, as the enzymes is what makes the ATP work, and therefore less energy, so less contraction at the muscles. Then the hydrogen ions accumulate, and the acid in the lactic acid, which interferes with the electrical signals in the muscles, and it slows reaction, so therefore decreasing performance. A way athletes sort of combat fatigue is soda loading, where they either drink or take some supplements of sodium bicarbonate before exercise, which increases performance as it helps buffer acidity and reduce the acidity, allowing the enzymes to continue to work. But it does have some negative side effects such as vomiting or diarrhea, and as you can see in the graph, that the athletes that's taken bicarbonate soda, even in pre-training, there is a small difference at a higher time, and then definitely in post-training you can see a major difference, that the performance has been increased. And then there's glucose and glycogen depletion, and the glucose is needed in glycolysis because the glycolysis makes the ATP, which makes the energy, and if there's no glycogen, then that can't happen, so there's no energy. And as you can see in the graph, the light exercise is using less glycogen for longer, and then the moderate exercise is a bit in between, so it's using a bit but not as much, and then the heavy exercise, which is shorter duration, is using more glycogen. At the start, they're all using the same at the start, and then the heavy exercise is using less as it gets forward. The moderate exercise is using a little bit more but still less. Then the light exercise is using the most as it goes along. And then what you can also do to combat that is ingest glucose, so taking drinks or gels high in glucose. And as the graph shows, the athletes that took the glucose before exercise were able to get to, well, they had high glucose levels at the start, and those didn't decrease as much as the ones without, the controlled group. And then with the glucose ingestion, the blood glucose levels stay higher, which enhances the performance. The moderate intensity recovery, so the O2 deficit is much smaller, and the EPOC and O2 that are smaller as well, as less oxygen is needed to replenish everything. And it's the alactic recovery, and the lactic acid slow recovery component, the lactic acid removed. This takes 1 to 2 hours by oxidizing any lactic acid. Then 65% of that is transferred to the liver, converted to pyruvate, and then enters the Krebs cycle, converted into CO2 and water, which is easily breathed out as waste products. Then 5% of that lactic acid is converted into glucose through gluconeogenesis, which occurs in the liver as part of the Cori cycle. And 20% of the lactic acid is converted to glycogen stored in the muscles and the liver. And 10% converted into protein, which is metabolic demands, which is example increase in heart rate or breathing rate, which means there's more oxygen used to the muscles and areas that are needed to help recovery. Also, DOMS can occur, which causes myofibril tears, which leads to muscle swelling and pain. This lasts up to 24 to 48 hours, which impairs the strength or motion of contraction. Ways you can combat this and ease it, maybe, is to massage or use foam rolling, which circulates the oxygenated blood to get rid of the lactic acid. There's also cryotherapy, which is ice baths, and this affects the white blood cells, which impede recovery, so they stop them from impeding the recovery. The submaximal exercise, for example, some marathon runs, long distance cycling, or just mainly endurance sports with long duration. So this is a low intensity and long duration. You're using your slow oxidative muscle fibers here, and the fuel you'll be using is glycogen and a bit of carbs and a bit of fat stores. The waste you'll get out of this is carbon dioxide and a bit of lactic acid and some water, but then you get fuel depletion. So the glycogen used up, as you can see in the graph, will decrease over time. So the start of training, the glycogen levels are high, and then at the end, as time goes by, it depletes and gets lower and lower. It's the same, and as you can see in the other graph, at the start of training, you've got high glycogen stores, and then after, you've got less. Then if you train the next day, the glycogen stores still haven't fully replenished. Then the same thing happens, is that at the start of training you've got more, and then at the end you've got less. Then it happens again that it hasn't fully replenished until day 4, where you should be resting, really. And then the fat stores. In an RER table, this shows that the fat is as a primary fuel, and this benefit is it's twice as much as energy as the carbohydrates, and by using fat, glycogen isn't used up, so fatigue occurs at a slower rate. So as you can see, the fat in the intensity, at a higher intensity, it has less contribution to the total energy, but at the higher intensity it's got a higher contribution than the carbohydrates, which is an economical technique. And then, as you can see in the graph, the VO2 max, as more oxygen taken into the aerobic system, so this delays the lactate threshold. So as you can see, the marathon runner, the lactate threshold and OBLA is delayed and happens later on, where the sprint happens quite early. Ways you can combat this as well is glycogen loading. So glycogen loading improves performance in events such as marathons and long distance running. And the first step you need to do is to deplete the carbohydrates. So this is through exercising. As you can see there, it goes down. And then once complete, you need to start loading by eating a lot of carbohydrates after a bit of rest, and this will go up and up and up, and then you'll have higher glycogen levels.